Hello? Okay, great crowd. Right. Good afternoon, everyone. My name is Afnan Islam. I am from a company called Strain Measurement Devices, and we are experts in sensors in high temperature, high pressure, critical applications, ideally. So today I want to talk about a bit how these sensors are designed and how industries are usually focused on designing these ruggedized applications. So this is the heart of the talk in one picture. So pressure measurement is a relay race with kind of six handoffs. Um, Ideally, theoretically, pressure pushes on the diaphragm, that pushes stress in the substrate, which kind of causes a strain, and then which kind of observes the resistive changes around it, creating a certain bridge output that could be verified with the electronics. And a lot of calibrations are involved in all these processes. Um, but with every of these handoffs, there's a chance that the baton might drop, right? So ideally, what it entails is a great diaphragm on a sensor doesn't mean it will help with the film if a thin film crisps, or a great bridge doesn't help if the package kind of leaks. So we kind of have to understand that we gotta engineer all these parts when we are making these certain high pressure, high temperature applications. So at SMD and as industrial practice, everything starts with the substrate. And it kind of just does two jobs at the same time. It holds the pressure and it sets the thermal environment that the film lives in. In this slide, there are like four common choices which the industry practices on and which our company also kind of uses. Inconel is our go-to for high temperature applications on corrosive media. Its expansion rate is very close to the thin film that we do, and expansion rate is very critical here because we got to measure the thermal mismatches between the mechanics of the substrate and the thin film. So we choose different substrates based on the end application. And if we want something lightweight, we kind of start with titanium grade because of its lightweight capacity. And then we also can put in sapphire or ceramic for extreme corrosive resistance. But ideally, what we have to kind of balance out is the alignment between thermal expansion and the resistive sensors around it. My example here is with nichrome, but industrial practices also use Kapton and other resistive alloys. So next we'll look at how the film actually sticks to the substrate, because the bond decides everything about long-term stability. So this slide is about the thin film design choices, right? Glue versus sputtering, depending on what we want to use. An adhesive bonded foil gauge uses an organic layer between the gauge and the metal. And that organic layer kind of creates creeps under sustained load. It can adhere to moisture. Thermal stability becomes an issue. Long-term drifting can occur. But when we do thin film, we look into the bond interface, and it's an atomic layer bonding. We can do, and it could be sputtered, it could be chemically deposited, or it could be also additively done as well. What that allows, it skips the glue entirely, right? So the deposit of the sensing film is directly onto the substrate at the atomic level, which allows for no intermediate layer, no creep, no moisture path, and just an all inorganic stack. So the number on the right kind of tells the story, like depending on conditions, if you choose between adhesive and then bonded straight gauges, you'll see a 10 to 20 times improvement, but cost comes into accountability here. The gauge factor is depending on the resistivity, is always very similar, but it could be worked upon. What these kind of sensors are looking at is reliability and stability over higher sensitivity. So let's look at the how we design these strain gauge, the pressure sensors themselves, right? So designing a high pressure diaphragm is a constant fight between signal and survival. If you look at the two equations, when designing the sensors, we kind of have to balance out like how much we stressing the substrate. Is it in a region or is it spread out? So that's kind of what you have to look into and count that as a variability when designing your sensors, and aligned with subsequent tests and experiments to set that up. So peak stress scales with pressure and gets much worse as the diaphragm gets wider or thinner. And that kind of explains the first equation, right? And maximum deflection is kind of a bit more dramatic. So ideally, if you think about it, if you look at the bottom left figure, if you kind of turn the knob a bit on a certain region, you're going to see all this variability. And depending on that, we kind of have to look into the peak membrane stress, the center deflection, and subsequently the burst safety factor as variables when designing, and keeping in mind, like when manufacturing comes into play, the number of manufacturing that we are playing with, right? Just by playing around with these ranges, the geometry and the gauge factors, like we at S&D, we can do between 20 bars to 50,000 bars range, and these are different range capabilities that we create design factors for, which is super important for after we do thin film. So next, we'll look into the bridge mechanics and how mechanical strain becomes a clean electrical signal, right? So after we have designed and process optimized all these parameters, and this is even before these are all before electronics have been established, and this is the first time we think about electronics at all, right? And it's a fundamental concept. I'm assuming a lot of people here comes from electronics background or mechatronics background, and they have the understanding of a Wheatstone bridge. So all these things that we're looking at, we're trying to cancel different errors, right? And the Wheatstone bridge kind of helps elevate after the mechanical parts come in. So in plain language, the Wheatstone bridge has 4 resistors, and they're all, we do vapor deposition, but of course, there are different methods it could be put in. And the 2 halves of the bridge pull in opposite directions. And when that happens, stress and strain occurs. So it's very important how we put in the thin film strain gauges and the Wheatstone bridge around it, because it has to be manufacturable, which means that it has to be repeatable in thousands of batches. And the deposition techniques have to be controlled. It has to be controlled while for manufacturing, not just for R&D purposes, right? So to do that, the whole sensor kind of has to work together. But certain changes can create issues. For example, if the sensor, if the Wheatstone bridge gets hot, every resistor will see temperature changes. But if they, theoretically, if they're changing temperature at the same rate, it kind of cancels each other out. But what a sensor manufacturer like us do, we also control the variability of these Wheatstone bridges, and we temperature compensate for each of these pads as well. So there's some compensation that takes place, and we're aware of it before we even architecture any software, right? And to do that, we use certain photolithography techniques. A lot of people use certain laser techniques, annealing techniques, and we kind of have to do it at sub-micron capacities so we can optimize it better. So a perfect sensing die falls ideally, if we can't create a perfect sensing die, the entire package would fall, right? Which we are going to discuss next. So till now, what you've seen is literally a pressure sensing element on a substrate. And then comes when you're trying to make a transducer, we need to think about the packaging of it, right? Packaging is not just housing, it's kind of part of the measurement system. So on this slide, you're seeing 6 layers on the left, the welding, the hermetic header, the cable lead-out protection, chemical washdown resilience, thermal excursion survivability, and we have to qualify all that stuff as well. So welding, we kind of have to hermetically seal it, and it allows us to make autoclavability of these sensors. We encapsulate, we do glass to metal or ceramic to metal headers to protect the cavity and encapsulate the sensors. For strain relief, we have cable exit. It's designed in a certain way that prevents anything coming in or ingressing. So you see, there are different transitions happening within the package, and what we kind of have to do is within every transition while packaging, other than the sensor element, we kind of have to create a variability and some test parameters and qualifications, so we can understand and put it into a design aspect when designing these high pressure, high temperature applications before even calibration comes into play. Right, and to do that, we kind of do a lot of testing capacities and design objectives. We have to set something up. So we do tests around long-term seal integrity, the zero ingress, which I've talked about, and the signal fidelity around it too, while doing some thermal cycling and fatigue testing on these sensors. So in the next slide, we're going to talk a bit more about the full validation of these sensor packaging interconnections. So 3 key technologies on the top you're seeing. One of the things we kind of work with heavily is the sensing element and the pads that connect it to the rest of the electronics. So we do gold wire bonding, which gives us a clean, fine pitch interconnect with no organic intermediary. We do hermetic headers, which gives cavity protection, and we do peak and similar high-performance polymers on top of it, which gives us a chemical and sterilization compatibility in the medical applications, or aerospace or defense-grade applications. And that allows us to play around with the temperature ranges too, even though there are different strain requirements. So, for example, high sensitivity strain requirements would have a lower temperature stability, but playing around with the packaging, we can increase the temperature stability of this entire thing. So thermal coefficient factors can be reduced, right? And on the bottom stack, what you're seeing, some of the validation and test capabilities that we have and we perform, so we kind of make the sensors as robust as possible. Right, we do thermal cycling, we do electrical characterizations, insulation, resistance, autoclavability when relevant, leak testing. One we do is helium testing, or inert gas testing, full traceability. Again, now this is more of a manufacturing and then inventory management, where we do full stack testing with correct serial numbers, right, for every sensor and every iteration of these sensors. And we provide the calibration certificates for it as well. So every sensor matches the correct calibration, and of course every sensor is different. So if the sensing element has to be in micron or nanoscale resolution, that can be optimized for every sensor, right? So, but ideally the point is we validate the assembly process and not just the development process, right? And that allows us to tackle what happens to the assembly over years of service, right? Now, so talking about years of service, one of the key issues these sensors face is long-term drift, which I'm going to talk about next. So thermal drift is well known in the sensor platforms, and it's ideally in my understanding, it's a materials problem first and a calibration problem only after the material problems are being sorted. So we heavily look into long-term drifts, and like on the left, there are some drift drivers. There is a residual film stress, interfacial stress distribution, thermally activated microstructural changes that we look at, and then package-level mechanical settings, right? So the chart on the right shows the result of these drift drivers and the optimization after we perform. So let me give you an example of how one of these drift drivers works. For example, the residual film stress. When we do thin film on a substrate, if following my previous slide, if the thermal coefficients don't match, it creates a stress and strain on the substrate, which we call the phantom strain. And that is usually not looked into calibration until you are looking for it for extremely high resolution. And think about it at high temperature applications, and you're looking at high resolution at high temperature and at a certain pressure range that you want to validate. So if we don't kind of figure out that these drifts happen, we don't necessarily know over the long term. After 2 years, you won't see the drift. And your sensor is going to, like if you are expecting a sensor to perform for 30 years and 2 years after it's starting to drop on results, you wouldn't be able to figure out and condition monitor for a very long time. So we kind of have to look into these elements, and we do this. We check the Arrhenius equation, which kind of explains the trick. So just to mitigate that residual film stress, what can be done is before sending out these sensors, you can anneal them in-house. So you can deliberately vacuum anneal them in the factory, and age them and calibrate it accordingly. So if that process exists, it kind of eliminates all of the residual stress that appears over a long period of time. So we do, like, when designing the sensors, you must keep in mind that these drivers are super important, and that has to be established into the manufacturing stage in quality, and calibrate and certify it according to certain standards. For aerospace, it would be AS standards. For medical, it would be ISO grade standards, and it has to be calibrated accordingly. In the US, we follow that. And in-house, we have that calibration capacity. So when you do this, of course, it depends on the requirement, but if you have the adhesive foil gauge that we talked about, you would see the drift, like it's 0.5 percentage full scale per year. And that is very normal. That actually defines the prices of these strain gauges. You can find it at less than $1, or you can find our sensors, which could be much more expensive, but you would see 10 to 20 times improvement compared to even other standard thin film processes. So that's where the price difference comes in when designing these high pressure, high temperature applications, pressure sensors, which are validated from strain gauges. So after we engineer that aspect, we look into the thermal calibration and cycling aspect, when we're looking into autoclavability or certain things. So we kind of do a few tests to do the active thermal calibration. So say we keep temperature at a certain level and we do pressure cycle, or vice versa, we pressurize the sensor. We also do negative pressures, by the way. We do temperature cycling around it for X number of times. And that also goes into our calibration reports for the sensor to go out. So once we have that process soaked in, and like if you are into the sensor background, you would know that there are like multiple different techniques. I'm sure everyone follows. There is the temperature soaking platform, the pressure sweep, and we kind of fit it into this polynomial, and this calibration model kind of integrates all these autoclave, like the number of ranges of tests that we perform. So once we perform all these tests, we have an error target band that we talk with the customers, and like we validate it, and we flash and verify this before the sensor is ready for the next steps, right? And we kind of talk to the customers about it, like if there are some issues which they should be aware of while designing these sensors, because every sensor is very custom for their own application. So there are multiple iterations between when designing the sensors, and usually you can buy off the shelf, but these are extremely customizable, and you have to talk to the manufacturers like us and work with them to build your application for longevity, right? So those were all the engineering things that we have performed, but even after that, there is an honest accounting of what error is left after all these processes. So the formula on the top left, it's, as you can see, it's a contribution. The contribution comes from sensor physics, thermal residue, the electronics, and then the calibration and traceability around it. And we kind of meticulously look into these, into all the data from the manufacturing, and of course you can, and we have to optimize this continuously through our manufacturing engineers. So it's very normal that when we are doing, say, when we are vapor depositing the thin film on whatever substrate we choose, that there would be an error percentile, and that is where the sensor physics and the gauge factor will not be. For every sensor, it might be a bit different. Well, of course, we try keeping it at the same stage, but it changes, to a certain degree. So if that happens, what do? We don't throw out the sensor. What we want to do is we want to optimize the results in later stages of manufacturing. So, for example, in the electronics noise process, if there's a certain degree of noise, we can cancel out that noise using software algorithms. But knowing the fact that there was an error issue on the hardware thin film deposition part. So if we can optimize those, we can keep within the expected results before shipping it out to the customers. Right. So that's pretty much how we do our things. And we have been establishing sensor techniques for the last 30, 35 years as a company. And we have created hundreds of different applications, and some of our applications are in the pressure sensors, and some of the, of course, these are based off in strain gauges, on which we are experts in. And we have moved into applications in the medical areas, in the conductor fabrication, oil and gas drilling, weighing and loading cells, and then we have a new line, fluid control, which I'll talk about in a bit. But strain gauges has allowed us to move into load cells and weight scales, and these are all applications we have built around for different customers. With our know-how, we have started a liquid flow, and in the medical world, we call it bubble sensors using ultrasonic. So we have started this ultrasonic line with the same established processes that we know of. So that has allowed us to create different avenues of sensing requirements. For example, in the medical industry, autoclavability and sterilization is super important. We kind of help there. We develop the sensor accordingly, and we use the same know-how to create high temperature and high pressure applications. Or if you are in a very extremely chemical corrosive environment, we can provide the sensors for that as well. So having that capacity and having the manufacturing knowledge kind of allows us to do what we do, right? So let me leave you with the core idea. if you only remember one sentence from what you have gathered today, and of course we can talk about it later on, let it be this. So calibration confirms performance, but materials, mechanics, and packaging are what create the performance in the first place. So if you keep that in mind, I'm happy to take questions at this point. Right. Thank you.